Hello again, and welcome again to Advent of Code in F#, day 11, part 2. Because in the last video I was getting really hung up on the explanation for the second part, and whenever I get stuck in like examples, there's only one way out for me, and it is this. I don't know if you can see it that well, but it's noodling my way around and drawing a lot of examples to make sure I understand what's happening. And I think I kind of cracked the code, or I cracked it enough to start programming again. So I'm just putting on my camera and let's do this together. I was having a lot of trouble with the rotating of the waypoint relative to the ship. And this is, for example, rotate right 90 degrees, as in the example. Yeah, rotating 90 when the waypoint is at 10 units east and 4 units north of the ship. And if R90 rotates the waypoint 90 degrees clockwise, yes, then it ends up at 4 units east and 10 units south. So this is, I kind of drew it on the whiteboard here, so it drops to here. And I did this for like a rotation of the same like relative position in every quadrant, and then I did it for 180 degrees and for 270 degrees, and I came up basically with a lot of test cases that we can use to drive our algorithm. So that is exactly what I'm going to do first. First I'm gonna figure out the rotation, because that's for me the hardest part today. In order to do that, if we look at our current rotating function, it takes a state and it takes like a direction, right or left. Yes, that's also relevant here. And then it takes like how many degrees. That can all stay the same. But the only thing that will kind of change is the state, because the state will always also have to take into account the relative position of the waypoint. So yes, let's add that in there as well. I'm thinking how I'm going to do this incrementally, because I just want to focus on the rotation part right now. Are we just going to leave everything as is and just implement the rotation first? Yes, let's do that. And then we can move everything and everything will fall into place just nicely. So let's forget about everything about the problem we know, except implementing a new rotate function, which will rotate our waypoint. I'm going to call this rotate waypoint for now. And we'll also return a, no, let's not return a state, let's return the new, let's return the new location of the waypoint. So let's return something like 0, 0 for now. And we can like inline this with the rest of the handlers in a second. Yes, let's do that. Okay, so is this the correct signature? I don't know. Let's see what we need. So for the first example from the exercise, today's exercise is like rotate right. Is this still? Let's look at what we did before. So rotate left, right, yes. And then the state. Don't know what we need here. We only need like the current location of the waypoint. So in the example, that is 10.4. Is that all we need? I think that's all we need. And that should be the example 4 minus 10. So there we go. And it's not rotate, it's rotate waypoint. So rotation, yes. Waypoint location, and it should give us a new location for the waypoint. There we go. 10.4 should be 4 minus 10, right? So 10.4 should be 4 minus 10. Yes, that is correct. Okay, so this is one case. I kind of think I know what to do in my notes here. So if I drew every possible rotate right and rotate left thing, It all turned out to be the kind of the same thing you had to do. Yes, but let's do rotate right 90 degrees first, and for now let's just use pattern matching as we did before. So let's match on rotation and the value. We also need the value. So rotate right for 90. So actually this is an instruction. Let's pipe in the entire instruction, yeah. Action is, what's it called? Rotate right. Oh no, yeah. I'm getting confused. Let's just do right 90. Forget about it. We'll clean it up if we need to clean it up. So we need to rotate to the right 4 degrees, which is 19, 180, or 270, and this is the current location. Yeah, so let's match on rotation and degrees as we did before. And if it's right 90, we can like do this. Yes. So match what's not okay. Is it R? Right. Okay, I have to be consistent here. Right is like one of the 4, or one of the 2 rotations. Yes, that's all we need. So we can rotate to the left or to the right. Yes. We give a number of degrees and a current location of the waypoint. Yeah, so this is like the broad stroke plan. So yeah, this is a hard-coded result, but it's saying, okay, it's a good match. So I'm gonna do a couple of rotate rights to make sure I cover enough of my bases. So this is an example of rotate right that was from the website. Another example of rotate right is if we are at this new location, 4 minus 10, where do we end up then? So we are now here and we end up somewhere here. So that is minus 10, minus 4. So this should land us at minus 10, minus 4. And there's already a pattern emerging, like we always swap like the x and the y coordinate, and a sign changes. But there's 2 more, so let's do a rotate right 90 for this. And that should land us at minus 10, minus 4, should land us at minus 4, 10. So again, we swap x and y, and we change the sign. Yep. Let's kind of line these up a bit. It's not really lining up, but okay. And let's do, for completionist's sake, let's do a final rotate right 90 degrees from where we are, and we should end up again at 10, 4. So stuff like this, like if you rotate right 90 degrees 4 times, you should end up at your ending position. This is a great place to use property-based testing. I'm not sure if I'll do it today, but if you've heard of property-based testing before and want to play around with it a bit, this is a great, today's exercise is a great, or the rotation part at least, is a great playground to try out property-based testing. But anyway, these are the cases for rotate right 90 degrees, and they are failing hard because we hard-coded the result. But as I said, there's this kind of pattern. So let's extract values from the waypoints, or let's keep this here so it's clear what we're expecting, and let's extract it in here. So now it's a pair of x and y coordinates, and we kind of flip x and y, so it's y and x, but we should change the sign of the resulting. Actually, is it true? Are we changing the sign? Yes, we changed like the resulting y coordinate sign. So 10, 4 becomes 4, 10 flipped, and we change the y direction. And again, if we rotate right 4 minus 10, it becomes minus 10, 4 with a 4 flipped. So let's flip the new y coordinate by multiplying it by -1, and I think that is rotation of 90 degrees implemented. Let's see. Yes. For left, let's do one example for rotate left, but it's almost the same, so we can go a bit faster. If we rotate left and, for example, take the 4 minus 10, so that is actually the inverse of this. This is 4 minus 10. We should, and if we rotate left, we should end up at 10, 4. Yeah, so we should end up here. This will crash right now because we are not doing anything with lefts. But if we have to rotate left 90 degrees, what do? We swap as well. So we swap x and y, but instead of like changing the direction of the resulting y, we change the direction of the resulting x coordinates. So it's kind of like this. I'm gonna try every case, but if it works for this one, okay, we're good. So this is rotating 90 degrees. Yes. Rotating 180 degrees is actually simple, or simpler. So let's give that a try. Rotate whatever 180 degrees. Left or right, it doesn't really matter if we rotate by 180. It's just like make a half turn, or like do a 360 degree arc around the ship. So this becomes minus, wait, I have the example here. So 10.4, rotating it 180 degrees ends up at minus 10 minus 4. Let's see if that's correct. So if we end up at 10.4 here and whoop, we flip it, we are at minus 10 minus 4. Yeah, that sounds correct. So we just change the signs of both x and y coordinates. So if we do whatever, left or right doesn't matter, and it's 180, we just change the signs. Change the signs, sides, not sides, but signs. So it's -1 and -1. I think this is rotation of 180 degrees figured out. Yes, that's done. And then we have the last part of rotation, which is the 270. So for example, if we rotate right for 270 degrees, that's actually easy because that's the same as rotating left for 270 degrees. And again, this is a very good use case for property-based testing, because now you could say in theory, well, you know what, I've mentioned it twice, I'm not gonna do it, and if I'm do it, I'll do it like off stream and show you tomorrow. But if you haven't heard of property-based testing, I owe you the courtesy of showing it quickly. Is there good documentation? That is actually a good question. Yeah, so property-based testing, I think it originated in the Haskell world with the quick check library, and in F# you have a couple of property-based testing libraries, but I think the most commonly known is fscheck. And let's just dive into an example. Quick start, sure. What does fcheck do for us? Instead of writing our test cases as we have been doing, like this is one specific scenario and this is what I expect as output. This is like example-based testing. In property-based testing, you do something else. You like write a generic property that's always true, or that's supposed to be always true. So it's kind of like an invariant of your algorithm. So for example, here, if you are looking at list reversion or the list.ref function, you could like write an invariant that reversing a list and then reversing it again, it should end up as the same list. And that's what's happening here. So this property, this ref is original, says that if I reverse a list twice consecutively, then it should end up as the original list. So this is just a predicate or a function that takes any list and it just states a truth, or it states a property. of the list.rev function. And what does fscheck do for you, or quick check in Haskell? It just basically generates a lot of random data. So in this example, it generates a lot of integer lists, and it tries to disprove your statement. And if it can't disprove it, it says like, okay, yeah, that's a scientific truth, a mathematical fact. I can't find a case that breaks your property, so then it's good. But if it's not true for a case, it will give you like a report of a small example showing you in what kind of or for what input list it's failing. So we could use this actually to do our property-based testing here, but let's do that another time. We are actually just solving the advent of code puzzle. So this was a not so quick detour to the world of property-based testing, and we don't even get to dive into it. Yes, I'm that kind of person. I'm sorry. This is a teaser. So we were rotating, and I was talking about a shortcut for rotating 270 degrees, because rotating right for 270 degrees is actually identical to rotating left for 90 degrees. So if we rotate right for 270 degrees, starting from, let's take the left 90 example, so starting from 4 minus 10, we should end up in the same as the left 90 case. So we should end up in 10.4. And this will fail. I hope this fails. Yes, it's even failing hard. It's saying like, ooh, you're not pattern matching on every possible case here, buddy. So yes, we're not matching on the 270 case. Let's match on the 270 case. And does it matter if we do right or left? Yes, it kind of does. So let's also match on right 270. And now instead of like doing the mental gymnastics and drawing it out, I'm gonna do the shortcut we just mentioned. I'm literally gonna do it, and that's like calling ourselves and saying like, instead of rotating right 270, let's just rotate left by 90. Sorry. And this will just like recursively call itself, and we implemented the left 90 case, so this will work out just fine. So I'm thinking this is rotating right by 270 degrees. Yes. Now let's quickly add a case for the left. Left 270 should be right 90. So there we go. This is rotating 90 degrees, yes, 180 degrees, yes, and 270 degrees, yes. So I think we have our rotating function defined. And it took me way longer than I care to admit. Yes, if the match fails, we'll get a runtime error, but we also had that in the previous rotation function. So this is what we want to do. Let's make some room. This is what we want to do, and we want to kind of rotation degrees waypoint. So yeah, rotate 90, that's the value below here. And we kind of want to take in a state, but the state doesn't really matter in this case. But what we do want to do is return a new state so that it lines up nicely with all the other functions. Yeah, let's have this function return a state. And if we're touching state, maybe let's take a look at state. It's currently contains the location of the ship. We still need this. The orientation of the ship is not that important. We actually need the relative position of the waypoint. So this is the relative position of the waypoint. And let's put that in the initial state, because otherwise we get compiler errors. We're missing a field. What's the initial state? Where's my advent of code? Let's get rid of this. Where's my advent of code? There we go. What's the initial point of the waypoint? There we go. The waypoint starts at 10 units east and 10 units east and 1 north. So that is 10, 1 in our XY coordinate system. So that is 10, 1. Waypoint is at 10, 1. I'm thinking, should we get rid of our orientation? Maybe not just yet. Let's keep it in and remove it once we refactor all our other code. So rotate waypoint is good, and now our state knows the waypoint's location, but we never update it. And we have to update it at several points, but let's start with rotation. So rotation. Rotation, this is the left or right, value is the 90, and state is the current state. So let's calculate a new location for the waypoint, which is what rotate waypoint does. Is rotate waypoint, given the rotation and the value and the state.current waypoint. So this is the new waypoint, and let's return the old state with the updated waypoint. This is actually all our rotate function should do. There we go. So this is the new rotate behavior, and it lines up with the original code, so that's cool. Forward is also different. Yes, forward is also different, because with forward movement we have to take steps towards the waypoint, and the value we get for the forward instruction, like forward 10, means take 10 steps in the direction of the waypoint. So take 10 steps into the direction of the waypoint. You know what, let's write a test for that as well. So in this example, let's try to execute F10, and we start at 0, 0. So let's write a test for that. So test forward, which takes a state and a value. Yeah. So a state and a value. Let's just use initial, and a value is 10, and we should end up somewhere. So that's also a state. But we don't want to start with the initial. We want to start with the initial state where our waypoint. Oh yeah, for example, for this test, it doesn't matter because it is the initial. Initial has like a. No, let's make it explicit. It's clear if it's explicit. So with waypoint in 10, 1. Is it 10, 1? Oh, 10 east, 1 north, yeah. So that's actually, this is doing nothing because initial has it, but now in the test it's clear. And location is also pretty important, so let's, is it not location? Yes, it is location. And let's make it very explicit in this test that we are starting at 0. And if we take forward 10 steps, we should end up at a different state. Yeah, let's copy paste this. So we should end up somewhere else. The waypoint should keep the same relative position, yes, but our current location is not 0, 0, but 110. So 10 times the step. There we go. And this probably fails hard. Yes. Wow, it doesn't even know the label. So let's load our code in and let's see why it actually fails. So it's actually failing for because we don't implement, or part 2 requires us to implement forward differently. Yeah, so this is taking the forward step. This is a test for it. Let's now try to implement it. Do we need the current location? We sure as hell do. And we also need the waypoints relative position. So let's call that like a delta. There we go. And we update the location. That is true, but the new location is just apply the waypoints delta value times. Yes. So it's x plus value times the waypoint and y plus value times the waypoints y. There we go. I think this is moving forward. So for our example, if it's 0, 0 and we start at 10, 1, we should take 0 plus 10 times 10 is 100. Yeah, I think this is it. Let's go. Let's see if our current example works. Yes, our current example works. So I think moving forward is implemented. Let's go take it from the top. So yes, initial state is correct. Parsing remains the same. Rotating is our new rotate function. Forward is our new forward function. Move is something we still have to do because moving does not change the ship, but it changes the waypoint's relative location, right? North 3 moves the waypoint 3 units north. Yes, north is affecting the y coordinate, so from 1 north it goes to 4. Yeah. So this is actually becoming easier. So move, orientation. We don't need to know the state's location. We need to know the ship's location. We need to know the waypoint's location. And we update the waypoint. What is the next location? We need to still match on the orientation, that's true. And then we need to update the next location of the waypoint. Yeah, so this is correct. Is this still correct? If we move north, we increase the y. Yes, if we move west, we decrease the x. Yes, so this is, I think, correct. Does this mean that we are finished? I think it might mean we are finished. It doesn't crash, so that's a good sign. Our waypoint ends up somewhere and we end up somewhere. And what do we need to provide? Manhattan distance between the ship's location and the origin where we started, so it's the same. It's just this plus this. There we go. Yay, we did it. So actually this was a fun puzzle. The only problem I had was the struggle with rotating stuff. My brain is not wired for like purely mathematical rotation magic. So let's quickly go over what we did. For part 2, for part 1 we just implemented like a fold and we ran every instruction. For part 2 we had to tweak what the instructions meant, so that also impacted like the state we needed to keep track of. Now that I see this, orientation is like not needed here, so let's get rid of it. Bye bye. Yep, everything still compiles, we still get the same output. Yes, so okay, bye bye. So for part 2, what did we do? We kind of had to change all those handler functions so they update the state accordingly. And most of the changes happened on a waypoint. Only the forward thing kind of took steps in the direction of the waypoint. So this like generic approach using folds and updating states and having a single function pattern match on all the possible commands and then dispatching to helper functions is something I do for a lot of these puzzles, and it's a really, I find it at least a really declarative and clear way to show you what happens. So this is like the one thing. No, you need to know what a fold does, because otherwise you won't understand like the main loop. But if you know what a fold does, you can just look at this function and say like, okay, this is what happens when we get a north instruction or a right instruction. So it's a really clear way of expressing command interpretation or executing commands. So it took me a bit longer than expected, and it took me 2 videos to solve both parts, but there we go. I hope you had fun, and I'll see you next time. Bye.